In this talk, Miguel and I will be presenting joint work with Board Kock, Giulio Malavolta, and Peter Schwabe. My name is Phillip Gajland, and our paper is called SWOOSH, Efficient Lattice-Based Non-Interactive Key Exchange. So here we have the Diffie-Hellman key exchange that we all know and love, and it's widely deployed. The problem is it provides no post-quantum security. So we would like a post-quantum replacement. And a lot of work has been done towards this end, but most of the work has been done on chems. So as part of the post-quantum competition by NIST, we've been looking into chems, but what about non-interactive key exchanges? Well, there's this folklore that says lattice-based non-interactive key exchange is impractical, and we even have some impossibility results that corroborate that. Now this work can really be summarized in this one line: it's not that bad. So basically, previous works have considered non-interactive key exchange in a sort of asymptotic regime, but we looked at concrete parameters and get something that's okay. So let me start with a brief outline for the short talk. So I will first talk about Nikes and chems and the differences and various applications. And then I'll present our scheme that we called SWOOSH, the passive variant, because there are two variants. And then in the second part of the talk, Miguel will talk about parameter choices that we made, talk about some implementation details, and finish off with a comparison. So let us first consider the primitive from our work. This is a non-interactive key exchange, or Nike for short. The way it works is you've got Alice on the left, Bob on the right. Alice will generate a public secret key pair, SKA, PKA, and broadcast her public key. Now Bob will do the same. He also generates a key pair, SKB and PKB, and broadcasts his public key. Now, without any interaction, Alice can use her secret key along with Bob's public key to derive a shared key, KAB. And Bob can do the same thing using his secret key and Alice's public key. Now, the Diffie-Hellman key exchange that we saw on the previous slide, that unfortunately provides no post-quantum security, fits into this category. On the other hand, we have key encapsulation mechanisms. So these are inherently interactive and two-stage processes. So how do they work? So Alice will generate her key pair and send her public key over the wire to Bob. And now Bob will run a probabilistic encapsulation procedure using Alice's public key. And this will output a ciphertext and a key. And he'll then send the ciphertext back to Alice. And Alice will then run a decapsulation procedure to derive the same shared key. Now the chems that have been the proposals from the NIST post-quantum competition, they fit into the second category. So classic Michaelis and Schwabe, they're of the second nature. So the first thing that we care about is, of course, correctness. So in the case of key generation, this is a probabilistic algorithm, and in the case of chems, we also have the encapsulation procedure, which is also probabilistic, and we want that Alice and Bob should agree on the same key. So the probability that they differ should be very small and close to zero. And the second thing that we care about is security, and at the highest level, you can just say, okay, the keys should be sort of indistinguishable from random. Okay, in most cases, you can just take your Diffie-Hellman key exchange and replace it with a post-quantum chem to boost your protocol to get post-quantum security. But in some situations, it might actually be very helpful to have a non-interactive key exchange. So some examples include implicit authentication when you use static Diffie-Hellman keys. So for example, in opt-TLS, you can remove the need for handshake signatures and remove rounds of interaction. Something that we've seen in the previous talk, asynchronous key agreement, messaging, X3DH, used in Signal and WhatsApp. There's been a lot of work in trying to migrate to the post-quantum setting, but one really easy way would just be to have a post-quantum Nike. Then there are other use cases of non-interactive key exchanges, for example, in radio networks for IoT devices, ad hoc score, group OS score, lots more. Okay, now let me give you a high-level overview of the protocol. So how does it work? So the lattice-based non-interactive key exchange works as follows. Alice will sample a secret key S, which is going to be some row vector of short entries, say of norm at most beta. And then her public key is going to be some LWE sample. That's going to be S transpose times some public matrix A plus E transpose. And Bob does the same thing. He also samples some secret key of short entries. This is now going to be a column vector. And his public key is also going to be an LWE sample for the same publicly known matrix A, and his public key is AS plus E. Again, they broadcast their public keys, and the shared key derivation procedure works as follows. Basically, it involves each person using their secret key and multiplying it by the other person's public key. Now, the important thing to note here is that the S transpose and E terms for Alice are going to be different to the E transpose S terms for Bob. So we need to run a deterministic reconciliation procedure to round those keys. Okay? And we're going to get some correctness error here. So we see this formula here. So I said that S and E are going to be vectors of short norm at most beta. A is going to be some square matrix of dimension n. And because we want to make everything as efficient as possible, we're going to be working over modular lattices. So every entry in the vector and matrix is going to be some polynomial of degree d. So the important thing to note in this formula is that on the top, you have to set parameters relatively large. You need a large beta, large d, large n in order to get hardness of LWE, because we want to reduce the security to the hardness of LWE. But unfortunately, we have to compensate by setting an even larger modulus to get correctness. So this is really the crux of the issue. And that's where the problem comes from. Now, it turns out that to get the strongest notion of security, we additionally need a stronger notion of correctness. This is something that we called semi-malicious correctnness in our paper. And it basically captures that Bob may choose his public key after having seen Alice's public key in an attempt to create a correctness error. And it turns out that we can satisfy this notion relatively easily by just adding some random scalar value that is the output of some hash function evaluated on both public keys into the reconciliation procedure as follows. And then we get a correctness bound that additionally depends on the number of hash queries that an adversary may make. Okay, so I said we have this stronger notion of correctness, and then we get different notions of security. Well, in the original Diffie-Hellman key exchange, we get this active security almost for free. You know, you only have to put the shared key into a hash, and that's all it costs. And this is really a result of perfect correctness. In the lattice-based setting, it's a little bit trickier. So we need, I said, semi-malicious correctness, so stronger notion of correctness. And then we show that you can use non-interactive zero-knowledge proofs of knowledge for the language, I know a corresponding secret key for the public key. And you basically just append a proof to the public key for this statement. And that's then going to give you the stronger notion of security. And in the next part, Miguel will talk about the parameters and the implementation.
So, as Philip mentioned previously, the choice of parameters determines not only the correctness and security that we get, but it also determines the performance that we are able to get. And in our case, there's three values that we want to look at. The first one is our prime modulus, and this dictates how fast our field arithmetic can be. In our case, we went for a prime modulus of size 214 bits, and this means that we need to perform something called multi-precision arithmetic, which is less efficient than if our field elements fit in a single scalar register. The other value that we want to look at is the dimension of our polynomials, and in our case, we chose polynomials of degree 256, and this dictates how efficient our polynomial multiplication can be. Finally, the relationship between the prime modulus and the degree of our polynomials also dictates how fast we can make the number theoretic transform, which is a technique used to optimize polynomial multiplication. So this is, we implemented passive swoosh, and this is the general overview of our implementation. And when I say we implemented passive swoosh, I mean we implemented only the passively secure version of the scheme, and we left out the non-interactive zero-knowledge proof of knowledge. This is important because when we introduce this zero-knowledge proof for active security, there's also a performance penalty that comes with this. So looking at passive swoosh only, there's three main algorithms. We have the setup function, which generates the matrix A. And this function is executed only once, and this matrix is then stored and used by the parties in the remaining functions. And therefore, the performance of this function is not particularly important. So the main two functions that we care about are the generation function, which generates the public and private keys. And this function is built on top of this polynomial arithmetic layer, and it then uses AES to generate the secret and error vectors. As for the shared key derivation function, which as the name suggests is used to derive the shared key, this is also built on top of this polynomial arithmetic layer, but it then uses C-shake to generate the random offset that Philip mentioned previously. So if we zoom in further, the main performance culprits that we identify on the key generation function are the polynomial multiplication, and here we care about the number theoretic transform, which takes around 10% of total execution time, and the big integer arithmetic. Additionally, we also care about the noise sampling, which is responsible for generating the secret and error vectors. As for the shared key derivation function, the main performance culprit that we identify is the random offset computation, which takes two public keys, hashes them together, and then generates a polynomial out of them. So if we zoom in further in the polynomial multiplication, the naive way of doing this is performing something called the schoolbook multiplication, which is quadratic, which has a complexity that is quadratic in the number of coefficients of the polynomial. However, lattice-based schemes use something called the number theoretic transform, which is way more efficient and has a complexity that is quasi-linear in the number of coefficients of the polynomial. Some other techniques that we use to optimize this is to perform the entity in place, which reduces memory usage, particularly important in the case of SWOOSH, which has quite large parameters. And by making the entity part of the scheme, i.e. by storing the matrix A and the public keys in the entity domain, we can pretty much halve the number of transformations that we need to perform. In the noise sampling, where the coefficients are sampled from the output of a pseudo-random function, and then in the random offset computation, where we perform rejection sampling on the output of an extendable output function, the instantiation of both of these primitives dictates the performance that we are able to get. In the case of the PRF, we use AES to 56 in counter mode, and for the random offset computation, we use C-shake to 56. So what does this get us? So if we compare our scheme to other post-quantum chems and Nikes and a Diffie-Hellman, a non-post-quantum secure scheme, if we go from top to bottom, looking at ECDH, an elliptic curve-based Diffie-Hellman, it is clear that this is the most efficient alternative. However, it is not post-quantum secure. If we move on to the two next rows, where you have Kyber and classic Michaelis, two post-quantum chems, these are clearly faster than SWOOSH and have, in general, smaller public keys. However, they require interaction. And as Phillip mentioned before, there might be cases where we prefer a Nike to a chem. Finally, if we move on to the two post-quantum chems that we have here, C-Tide and Nike, and SWOOSH, there's a clear trade-off between the key size and the performance that we are able to get. With SWOOSH having larger public keys, but also considerably faster key generation and shared key derivation function. So in summary, what are our main contributions? We provide a module LWE-based non-interactive key exchange with strong correctness and proof in the QROM. And we provide a generic transformation from passive to active security using NISIX. Additionally, we provide an optimized implementation of passive SWOOSH using Rust and Jasmin with parameters that achieve 120 bits of security against quantum adversaries, and that result in smaller public keys than that of classic Michaelis, and faster key generation and shared key derivation than C-Tide, another post-quantum Nike. If you're interested, you can check out our paper on ePrint, the code for passive SWOOSH on GitHub, and the talk that we gave at RWC earlier this year on YouTube. And with that, we conclude our talk.